In a tunnel beneath the nation's capital, a commuter train carries astronomer Benjamin Peary to work. In our urban society, there are few reminders of the natural world around us. Peary remembers a childhood in a small Minnesota town when the sky was always blue and the stars shone brightly every night. Today, through the glare of city lights, we often cannot see the stars above. Now a professor of physics and astronomy at Howard University, Peary recalls his first curiosity about the stars when he was a student.
As an undergraduate at the University of Minnesota, well, I had often looked up at the stars and wondered, what in the world might they be? Astronomy was not a large thing. The public had not discovered astronomy. Even physicists hadn't discovered astronomy. But when I was a senior, I remember I used to stand out in the frozen Minnesota night and look at those stars and grow more and more irked and embarrassed as a senior and physics major and not know what these things were overhead. I decided, on the basis of all this consuming fascination that I was developing for those icy blue lights up there, I discovered that there was something called astrophysics, and I decided that just had to be for me. Not many students have seen the stars, have really seen anything but a few bright lights out there. So that's a sadness that arises. The other thing that arises is that they're astonished, and they wonder why stars have different colors and all that. What are they? How far are they? Why are some bright, some faint? What are they made of? Why do they shine? And with a little prodding, we began to get just a flood of questions in order just to account for that amount of energy.
The thermostat, so to speak, helps control the rate of energy flowing out of the sun. Or does it not?
Yes, okay, it does.
It hasn't, that flexibility in temperature hasn't occurred in centuries.
Not dramatically.
Okay.
Now, that's the second point I want to make in just a moment.
At the nearby U.S. Naval Observatory, Peary introduces his students to the world of astronomy.
I can see how early astronomers got caught up in the poetry of the moment and the geocentric idea, and the heavenly bodies were perfect and circular motion. I can see how they got caught up into that, because when you look at the sky, if you lean way back and you just look at it, it's like this black covering with these different sparkly, designy, colorful lights, and they twinkle and they seem so perfect and so unmoving. And it's kind of like God made it just for, the earth, just to engulf the earth, So it is an interesting class.
Lots and lots of history there.
For Benjamin Peary, the telescope has been both an inspiration and a tool for discovery. As an educator, Peary hopes to share with others what he has witnessed personally. As a professional astronomer, there was a time when Peary enjoyed a privileged view of the lives and drama of stars.
A brighter star and a fainter star, and that's the way it used to be.
The stars we see in the night sky are only a handful of all that populate our galaxy, the Milky Way. Those stars appear unchanging. Like humans, they are born, they live, and they die. Within dark clouds in interstellar space, new stars are born. How this happens still has much mystery for astronomers. Most stars die quietly, gently fading. But some end their lives in a vast explosion. Their ashes, rich with newly formed chemical elements, mingle with interstellar gas to become the raw material of new stars. Our galaxy is just one galaxy among billions. The sun, our star, moves in the outer suburbs of the galaxy, in the curl of one of its spiral arms. As the galaxy rotates, it takes the sun 240 million years to make one orbit around the galactic center. And the sun, in its life, will make many orbits. The brightest stars in the spiral arms lead briefer lives. As the galaxy makes a single turn, there is time for many generations of these stars to live and die. We know that stars are born, but how? We know that stars explode, but why? We seek the answers because stars, planets, even our own bodies, are made from stardust.
When I go out in the night sky, in a place where you can really see the Milky Way, I rarely think of it as a scientist. I look at the Milky Way, it's the same impression that everybody else gets, and that's just, wow!
A father-son fishing trip on Chesapeake Bay is an opportunity for astronomer Leo Blitz to share his excitement and love of the stars. It is an enthusiasm that exceeds the bounds of science. For nearly a decade, Blitz has sought to unlock the secrets of the Milky Way. But the best-kept secret of all still eludes him. That is the mystery of how stars are born from the near emptiness of interstellar space.
We understand the life cycle of stars pretty well, except for that part which occurs when stars are born. When we look, even through ordinary light telescopes, at the space between the stars, it looks empty, completely empty. And the emptiness is really far from the truth. The space between the stars filled with matter, with gas. That stuff is really important because that stuff ultimately gets collected together by processes that we don't fully understand to form new stars like the sun.
To find a star like our sun at the very early stages of formation would be a significant advance in astronomy. For Leo Blitz, it would be the culmination of a decade of research. From the College Park campus of the University of Maryland, Blitz directs a major effort to solve the mystery of star formation. For him, it is a childhood dream come true.
I was one of those kids who, when they were in first grade and the teacher asked them what they wanted to do, I said I wanted to be an astronomer. It was a simple fascination with space travel, rocketry, the solar system. When I became an adult, I became a kid again. What greater enjoyment can you get than to do the things you wanted to do as a kid and actually get paid for it?
In the basement of the astronomy department, a dozen scientists recruited by Blitz seek to understand how stars form. He has nicknamed them the Group.
Oh, Jung-hee. Were you able to get any? What we've done is put together a group that has roughly 12 people. Everybody's involved in the process and getting involved in questions of star formation and in the research that we do. The deadline for proposals...
When Blitz arrived at the University of Maryland in 1981, he was the only person in the astronomy department working on star formation. As the inquiry accelerated, the team grew, and the need for communication became more critical.
I've got 3 doors to my office, and I expect people to be able to come in and use any one of them. We have a seminar every week. We get together every day for lunch. We're always talking science, and we're doing it not because we have to, but because we want to. That's what we think about. Is this going into the proposal?
No, this is actually for the paper.
Okay, so make sure that that gets done.
Okay, sure.
Do you have Hat Creek? Can you bring up?
All right, can you call me back?
We got to see what's going on at the site.
From a computer terminal in Maryland, Blitz and his team can direct by remote control radio telescope receivers across the continent at Hat Creek in Northern California. Signals received by the Hat Creek Radio Telescope could lift the veil of mystery surrounding the birth of stars. The light from stars can be detected by optical telescopes, but stars that are forming do not yet produce light. Instead, they emit radio waves, so a radio telescope can see into star-forming regions. A trio of radio dishes forms a single powerful instrument that Blitz uses in his search. The telescope can maintain a 24-hour-a-day vigil, scanning the star-forming regions of the Milky Way.
This is the Milky Way. This is our home galaxy. This is where we live. It's where we're always going to be stuck because we can't ever get out no matter what else happens. This particular mosaic is, I think, the best one that's ever been done of the entire Milky Way. What we have to do is imagine that we are the sun. We're standing on the Earth around the sun, and the Milky Way is all around us. And the region of the galactic center is right about here. The center is hidden by this dust, these dark regions, which were once thought, in fact, to be holes in the stars. And it's these dark spots that contain molecules and dust. And the stars that are forming inside of them. They're completely invisible to optical telescopes. In a few places, we can see that some of the stars are beginning to break out of this dark material, and that's just what's happening here. These objects are just now emerging from these cocoons in which these things have formed. Before I started graduate school, I was in industry, and my boss had, at the time when I told him I was going to graduate school, he said, what a life, all you have to do is just sit around and you think. And I discovered once I became a professor myself that was far from the truth. Typical days are 12, 14-hour days. There's teaching, there's writing, there's research. For me, there's running the group. And the most important thing of all is the time that I spend with my son. Hi, puppy. Come on.
Oh, you got a haircut.
Yeah. So throw this in the back. So we get to do this and they stay wet. Brian is with me half of the time, and it makes for a very full life. I try to cut out that amount of time that's left for purposeless things, although everybody still needs just to be able to goof off. The demands on my time recently have gone up. It seems to me that I need more than 24 hours a day, and yet there are none. And unfortunately, in the last year and a half, I've played no squash, and that's something for which I have a great passion. But the one thing I can't give up, I won't give up, is that time that I spend with my son. There's nothing that's more important to me than that.
Perfect.
While Blitz juggles life as father, scientist, and academic, he is personally driven by the desire to know how we fit into the universal scheme of things.
We look for the way in which stars form for several reasons. One is a quest for our origins. We live here on the Earth, we're a planet around the sun. We know from geological evidence that we've been around for 4.5 billion years. How did we get here?
To Blitz, the question of how we came to be, how a star like our sun was formed, drives the research effort forward. Each week, his star formation team meets to assess the latest observational data on the star-forming regions of the galaxy.
The most massive clumps here are these. They're all in the midplane of the cloud. Some of them have stars forming in them.
Team members have been handpicked by Blitz from the United States and 6 foreign countries. Among the International Assembly is a postdoctoral fellow from Holland, Eugène de Huys.
At higher frequency.
De Huys and Blitz are planning an observing run at the Hat Creek Radio Telescope Observatory. They hope to detect a star before it ignites, a protostar.
That's right.
But why
So
not?
then,
Because there's no surrounding medium.
In the coldest, darkest parts of the galaxy, a protostar is born from clouds of hydrogen gas and other elements. Radio waves reveal how the gas moves within the cloud. Mapping the radio waves produces a picture. Blitz and de Huys hope to discover a region where the gas is condensing to form the core of a young protostar.
One of the reasons that the existence of a protostar is so hard to really prove and so hard to find a protostar is that it's not really putting out its own light. For instance, like a star. I mean, a star is obvious, right? You can see it. So that's one of the reasons that finding a protostar is very difficult. Although if you could come up with a way to do it, that would really be extremely interesting, and that would be really a fantastic advancement in the study of star formation.
it's like trying to find buried treasure at the bottom of the ocean. What happens is that the blackness of the ocean just soaks up all the light. You might try to shine light from the surface and to try to illuminate something like the Titanic at the bottom of the ocean, but you can't see it because the light is all absorbed by the intervening material. And so what we want to do is to go up to Hat Creek and look in detail at one of the regions where we have some evidence from other observations that we have condensations that look as if they may be forming stars.
At the remote Hat Creek outpost, Blitz and de Huys will spend a week investigating a star-forming region called the Rosette Nebula.
The other sources are next to it. This is 250. It's about 1.5 times as
Oh, it's 17,
weak.
right,
Yeah.
okay.
For Blitz and de Huys, Hat Creek is a listening post, their stepladder to the stars.
2.1 minutes is what it gives us the error if it can't get a
there's
fit.
Yeah, there's something wrong.
So let's do this again
Yeah.
and do it with a longer integration time so that we get more
Let's do
signal.
20.
Okay, then we're
That's
fine.
nice.
We
So
can-
we'll let this one finish.
This one's
Because
fine.
star formation takes thousands of years to occur, Blitz and de Huys cannot witness the actual event of stellar birth. But radio signals can provide a snapshot of the process.
Right now, what we are looking at is the radiation that comes from individual molecules. We look particularly at molecules such as carbon monoxide, carbon monosulfide, CS, HCO+. We can see the motions of that material. And in some sense, what we're really doing is looking at the cold part of the universe. When stars form, they form out of very, very cold gas.
The Rosette Nebula is a bright region within a larger dark molecular cloud. In the glowing heart of the rosette, hot young stars light up the surrounding gas and dust. It has taken about 10,000 years for these new stars to blaze forth from their gaseous cocoons. For Blitz and de Huys, the search is not in the glowing and brilliant area of the rosette. It is in the surrounding dark regions of the larger molecular cloud. Blitz can imagine what takes place within that darkness.
If we were traveling through space and we could travel very fast, we would notice as we got close that this cloud of material breaks up into little pieces. And as you move into one of these things, what you might notice is that suddenly it becomes very bright because the star has begun to burn its nuclear fuel and very likely would have jets of material that are coming out, which are almost surely a necessary consequence of the star formation process. On occasion, we make discoveries, but really what we do is we create the universe in some way. And what I mean by that is we make observations. We see things here at the telescope, for example. We rarely look at things that have not been seen before, but we try to create order and understanding from what it is that we see. entire idea that stars form at all is only about 200 years old. How stars generate their energy, we now know comes from nuclear fusion, and that process was elucidated by Hans Bethe in 1939. It's the work that he won the Nobel Prize for, quite fittingly.
I was born on July 2, 1906, in Strasbourg, in Alsace, which was then German and later became French.
Cornell University in Ithaca, New York, is now home for the man who discovered how stars shine. It was here over 50 years ago that Hans Bethe calculated in detail how stars produce energy. His interest in stars arose from a wider curiosity about how the universe works.
I want to find out how the world is made. What is it made of? What holds it together? What makes it operate the way it does?
Growing up during the first 2 decades of this century in Frankfurt, Germany, Hans Bethe showed an early brilliance in mathematics and physics. He began his career as a lecturer in the German university system. Then the Nazis came to power. When he learned that his Jewish ancestry disqualified him from teaching, Bethe emigrated to England and then to the United States. He arrived in February 1935 to become an assistant professor at Cornell University. Bethe took to Cornell immediately.
I became a member of a very friendly group of physicists here at the physics department. I found it most satisfactory. I loved them, they loved me, so I stayed.
In 1938, Bethe attended a conference of physicists in Washington, D.C. The meeting had a profound effect on his life and work.
They thought it would be nice to discuss the nuclear reactions in stars, how the energy in stars was generated. Nobody knows really what nuclear reactions take place and what makes the energy. And that was something which I thought I could work on and might be able to solve.
Just 6 weeks of concentrated effort led Bethe to the answer. Bethe knew that the sun shines by nuclear fusion. Hydrogen, the basic ingredient of all stars, is fused into more complex elements. In this process, matter is changed into energy, according to Einstein's famous equation, E equals mc squared. Bethe's achievement was to determine the exact sequence of nuclear reactions that occur and the precise rate of energy production. At the center of the sun, every second, 4 million tons of matter are converted into energy. So massive is the sun that it takes millions of years for this energy to reach the surface, which rages at a temperature of 10,000 degrees Fahrenheit.
In this reaction, an enormous amount of energy is set free. Enough, certainly, to keep the sun and other stars going for millions and millions of years. In the case of the sun, for instance, it will last for a total of about 10 billion years. Once, when I gave a talk like this, one of the people in the audience asked me, did I say million or billion? And I said billion. Oh, he said, I'm relieved.
In the summer of 1938, Bethe published his discovery of how stars shine in a journal that offered a prize for the best paper. He used most of his $500 award to help his mother emigrate from Nazi Germany. It was not the only prize Bethe would win for the work he did that year. He was awarded the Nobel Prize for Physics in 1967. Soon after his discovery of how stars produce energy, Bethe and many other scientists saw that the conversion of mass into energy had awesome possibilities for warfare. Nuclear weapons were the result. In 1945, the atomic bomb ended the war in the Pacific. Soon afterward, the precarious world of the Cold War produced the most powerful weapon in human history, a device which uses fusion processes almost identical to those in stars, the hydrogen bomb.
5, 4, 3, 2, 1.
On February 23, 1987, an explosion was detected that was 1,000 trillion times more powerful than the hydrogen bomb. It was a supernova. A massive star had undergone a dramatic death. The exploding star suddenly appeared in the Large Magellanic Cloud, a companion galaxy to the Milky Way. It was the brightest supernova seen from Earth in 4 centuries. Because of its location, the supernova could best be seen from the southern hemisphere. The seaport metropolis of Sydney, Australia, became a gateway for astronomers from around the world who hoped to gain new knowledge about the death of a star. At the Anglo-Australian Observatory, researchers have followed the supernova ever since. The news of its first appearance will never be forgotten.
It was something that blew up 170,000 years ago, and the light has just made it to us.
It completely stopped dead all the other research programs that I was working on.
Peter was running up and down the corridors of Imperial College, knocking on people's doors, saying they've discovered neutrinos.
That was certainly nearly as exciting as the supernova itself.
Yeah,
yes,
I think
yes.
It's absolutely amazing.
Everybody who was involved remembers what they were doing, just like when Kennedy was assassinated. You remember what you were doing when you heard about it. And there was I happily down in that building over there, working on data, and suddenly came along, a colleague came and sat down and said, "Have you heard about the supernova in the Large Cloud?" I said, "No, I don't know about supernova." I was busy typing away. Suddenly started thinking, just a minute, supernova in the Large Magellanic Cloud? That's going to be visible to the naked eye. That's closer than any supernova we've seen for 400 years.
The supernova was destined to change the life of Mike Doppiter. Doppiter is an astronomer at Mount Stromlo Observatory in the capital city of Canberra. For 15 years, Australia has been home for Czech-born Doppiter, his French wife Patricia, and their son Igor.
Supernova 1987A is a real keystone for understanding stellar evolution. And this is really great because now we can put handles on lots of parameters of stellar evolution theory, which up to now have just been in the realm of speculation.
Like other astronomers, Doppiter remembers well the moment he received the news that a supernova had exploded and was actually visible in the sky above Australia.
Well, I was sitting down at the dining room table there, and I picked up the morning newspaper. And there on probably, I think it was page 3 or 4, because it wasn't considered very important, news, supernova discovered in Large Magellanic Cloud. I thought, man, that can't be true, for God's sake. And so I went and rushed up to Stromlo and discovered that they'd actually heard about it the afternoon beforehand, but no one had bothered to tell me because I was working at home.
Well, Mike comes back home and he says, "Oh, I've discovered something tremendous," and I hear it all the time, so I've become very blasé about it. So when he talked about the supernova, for me it was just one of his discoveries and nothing more.
Oh, it made a complete hash of my life. I was there happily going on doing the research that I was doing, and then all of a sudden this thing goes off, and I just simply had to go and start all over. First of all, I had to learn about what supernova were all about, because although I'd been working on supernova remnants. I never kind of dreamed that this kind of an event would actually happen.
Observing the supernova became a way of life. The flight to a remote telescope facility in Siding Springs, several hundred miles away, has become Dapita's regular commuter run.
We're flying up from Canberra to Coonabarabran, which is about 400 kilometres north, and it's sort of on the edge of the Great Australian Dry, where you get much clearer skies, much better conditions for observing, and it's a very, very dark sight. And so we've put all our largest telescopes up at Siding Spring, and I shall be observing the supernova because now it's 3 years on since the supernova went off, and the supernova has become very, very dim, and we can only observe it using the largest telescope. So I'll be using the 2.3 New Technology telescope. In addition, there is the 3.8 meter telescope, which is operated as a joint project between Britain and Australia, the Anglo-Australian telescope, and that will be used for infrared work. 3 years on now, and I'm hoping to be able to observe it up to about 5 years, 10 years. Well, I'll just keep on observing it and see what happens.
Hi again.
The frontier settlement of Coonabarabran is the starting point for the journey to the observatory complex through the rugged Warrumbungle National Park.
If it wasn't for supernova explosions going on through the 10 billion years that our galaxy has been in existence, we wouldn't have the elements that we need to build planets, and we wouldn't have the elements we need to build life. I mean, it really is true that the whole of the Earth and everybody on it is just a product of stardust.
Siding Spring Mountain is the major astronomical research center in Australia. It draws scientists from around the world. Many come to observe supernova 1987A, named for the year in which it appeared. Dapita and others want to know how, within the cosmic furnace of an exploding star, the rare heavy elements of the universe are forged. Without supernova explosions, there would be no Earth, no other planets, no life.
Well, supernova 1987A was really neat in that it chose to go off in the Large Magellanic Cloud, the nearest galaxy to our own. We know exactly how far away it is. And we have a kind of view right up out of the galactic plane, so we can see the thing very clearly.
Well, here's the telescope. We're tipped over looking at the Large Magellanic Cloud, and the light is coming from the Magellanic Cloud, its journey of 160,000 years and the extra 3 since it went off, to land in the mirror and be reflected and to be gathered in by our instruments. This telescope has been designed for maximum efficiency, plus the fact that the whole thing is under computer control, so that we can simply press a single button in the control room, just one single observer, and the telescope will come and track to the object.
The great thing about observing is that sometimes, you know, it's routine, it goes on night after night, and then suddenly you get something which is completely out of the ordinary, and then the adrenaline flows. And even if you haven't made a discovery, just the joy of the hunt at that point really fires you up and keeps you going for a few more hours. The supernova, I've been living with it now for 3 years. I mean, it's almost as if we were married. You get to know all the little bumps and wrinkles of the spectrum, and you see it gradually changing and getting old, falling apart, and eventually will become too faint and diffuse to observe. What I'm trying to do is monitor it over the years and understand the way it evolves. It's completely different from what it used to be even a year ago, and it's changing continuously. Ah, and here it comes. We've got neon 5, neon 3. There's the hydrogen lines. This is magnesium. This is one of the elements that makes rocks. This is the iron that was originally the radioactive cobalt. I can tell from this it's actually way down in the core of the supernova. This is really what I'm trying to get to. I'm trying to understand how the different layers of chemicals are produced in this supernova.
In the spectrum of the supernova, Doppler can read messages that tell of the star's short life and violent death. Most stars burn steadily for billions of years. Ultimately, they use up their nuclear fuel and quietly fade away. A massive star, one with 20 times the material in our sun, burns at a frantic rate. When its hydrogen fuel is almost exhausted, the burning accelerates. The star grows larger. Deep inside, nuclear fusion continues. At its core, the star continues to create and burn heavier elements, such as oxygen and silicon. Finally, at the very center, the star forms iron. But iron cannot serve as nuclear fuel, so energy production stops. And when the nuclear furnace shuts down, the core of the star collapses, setting off a gigantic explosion. A supernova radiates with the energy of 10 billion suns. All the elements the star has made, including those needed to make up living creatures, mix into the interstellar medium, enriching the gases and planting the seeds for new stars, planets, and people. While Doppler searches for stellar ashes created in the furnace of the supernova, others are seeking a far more exotic byproduct of the exploding star, an object called a pulsar. The hunt for a pulsar in the supernova remnant has started an international race among astronomers. One of the searchers is Australia's Richard Manchester.
I've been really working on pulsars for pretty well the whole time that they've been known about. So it's a challenge to find these things, and we've been fairly successful at it. The searches that I've been involved in have found about half the known pulsars. It's about 200 or 250 altogether, so it's been good.
Even for a seasoned pulsar hunter, there is no guarantee of success, because not every supernova event produces a pulsar. A pulsar forms from the core of a dying star. As the supernova explodes outward, the star's core is crushed by gravity and collapses inward to form a spinning, superdense object called a neutron star.
Neutron star is really an incredible object. It has the same mass as the sun, but it has a size of only about 20 miles. So you've got all the material of the sun compressed into a thing only about 20 miles across. Just to illustrate how dense that is, if you could bring a sugar cube of neutron star material to the Earth, it would weigh 100 million tons.
A neutron star can become a pulsar as it spins rapidly, generating radio signals in its strong magnetic field. Radiation beams sweeping through space like a lighthouse may be picked up by radio telescopes if the beams sweep past the Earth. Since the supernova first appeared, Manchester has used the 280-foot Parkes radio telescope to search for its pulsar.
Being a pulsar person, I thought there's got to be a pulsar in this thing, let's go and find it. So observed the supernova, which was very bright then, looking for a pulsar in it. It would have been really fantastic to find one, even though the probability of success at that time was pretty minimal, but had it come off, it would have been a world beater. It didn't, of course, and I'm still looking for the pulsar.
Before he trains the dish on supernova 1987A, Manchester fine-tunes his instruments on the well-known Vela pulsar.
So we'll type in the...
The Vela is a young pulsar, a mere 100,000 years old.
R1. Mount the tape. I think we've got everything set up now, so we have to go and look at a strong pulsar and see if it comes in okay. Beginning to go. And levels. Okay, well, let's see if we can get it on the audio. There it is. Vela pulsar is in a supernova remnant. The pulsar in SN 1987A might sound like this if we were able to pick it up. We need to go switch on the control system. This is going to take a while. Okay.
What's the reading?
5 and 3. We're going on to SN 1987A to see if we can find the pulsar there. We've looked many times before, so the chances of finding it this time are not high, but it'd be so exciting to find it that we keep on looking.
Any pulses from 1987A should be weak, and therefore are likely to be buried in a sea of noise. It will take Manchester months to analyze the data he collects tonight and to sift out the obscuring noise. Even if a pulsar does exist in 1987A, it may never be seen. Its beam could sweep across space, but miss the Earth entirely. But if the beam does not pass our line of sight, a pulsar could reveal its presence indirectly. Gas surrounding the neutron star would be heated by the rotating beam. So astronomers may be able to detect a pulsar from the glow of the surrounding gas. The largest telescope on Siding Spring Mountain is aimed at 1987A. David Allen of the Anglo-Australian Observatory is trying to detect the pulsar by the indirect method. He uses an infrared heat detector on the optical telescope.
What's happening to the supernova is fading. But if there is a pulsar there, that pulsar should stop it fading, should hold the energy and in fact cause the gas to appear hotter. And since we're able to monitor the physical state of the gas, we're looking for evidence that the gas is getting hotter as the rest fades away. You have to have one person who is self-sacrificing and watches it to tell you when to say no.
Tonight, Allen and his team will look at the heat radiating from the supernova remnant. Energy from a pulsar would be heating the gas around it.
The temperature of this liquid nitrogen is about minus 330 Fahrenheit. is even cold by the standards of places I've visited in the US, Alaska.
In order to measure the heat from a pulsar, Alan must make sure that the detector on the telescope remains cool. Heat from the detector itself could overwhelm faint signals from distant sources. Liquid nitrogen provides the coolant.
Now, the actual infrared detectors, and when we pour the liquid in, the detector is inside, attached to the metal that this liquid cools. And so it itself is cold. Right, this liquid nitrogen is actually cold enough that it freezes things like banana skins solid. As long as you're out of the way, you can get rid of it.
What do you want to do here? Do you want to...
I want to do an arc in a minute. That's come out the same there, right? Okay, let's go to the standard. So we haven't lost any data.
Well, you're running at 40 milliseconds? That's what you're getting.
Yes, gain 100 on the arc.
40 milliseconds.
That was fine. Okay, I'm going to put the arc on Steve's TV down.
As data is received, the supernova reveals a new, unexpected story.
You happy? Running.
We thought when we started we maybe would find some evidence of a neutron star, pulsar. So far, that's not working out. It's getting terribly hard to make these sorts of observations. We just can't say anything conclusive. But instead, we've bumped into something by chance. I mean, this sort of happens, you know. You can't predict science. What we've bumped into, maybe we should have thought about, but we're able to detect some hydrogen, the commonest gas in the universe, that hasn't previously been seen associated with this supernova.
The hydrogen that Alan has discovered is gas blown from the star before it exploded, revealing conditions within the star before it went supernova.
You never know when a star is going to become a supernova. They don't jump up and down and wave a flag and say, hey, I'm going to explode in 100 years. Right? So you never have a chance to go along and study a star in the expectation it's going to go bang tomorrow. The only way you can do it is to work your way back, having seen it go off, is to try and work out what was there beforehand.
By understanding what happened to 1987A, astronomers hope to determine which stars in our own galaxy have the potential to explode.
We know from supernova 1987A that stars that we thought previously were not really candidates for supernova explosion could go supernova quite unexpectedly. So we're now looking for objects which are like supernova 1987A. In our own galaxy, there is a star, famous star, Eta Carinae, which has varied in brightness enormously and blown off shells of gas. So this fellow's saying, look, I'm unstable in my outer layers. The real question is it unstable in the core?
Eta Carinae is the most luminous star in the Milky Way. It radiates as much energy as several million suns. Astronomers predict it will end its life in a supernova explosion, sometime within the next few thousand years. Supernova 1987A is helping to identify less obvious candidates, stars that may meet a violent end far sooner.
I think that the great thing about supernova 1987A is it teaches a lot of things. It was very, very exciting for a while there because you didn't know what was going on and you were hunting. It was the joy of the hunt. And then you found things quite unexpectedly that you didn't know existed. And that's the great thing about research. It's the hunt that's the thing.
In a case like the supernova, you know, had we found something, it would have been fantastic. The probability of actually succeeding was very low, but even so, the return, if we'd succeeded, would, you know, really would have been worth it. So even though the theoretical models may say, you know, there's no chance, I'll have a go. It's just on the off chance that they're wrong.
The supernova is a terribly important event for us. We wouldn't exist without supernovas, because in the early universe, only two elements are made, hydrogen and helium, and all the other elements must be made in supernovas.
I suppose one of the amazing things when you sit in a place like this and look around is to think that everything here, the rock, the trees, me, really came out of supernovae. A supernova is the only way we know to generate all of these complicated elements, the heavy elements that are needed to make a planet, a tree, a person, so that we're all children of the stars. These are supernovae that erupted before the sun was formed, more than 5 billion years ago. And they're debris that you and I, the mountains, are made of.
We think of the stars as lasting forever, but they don't. They may last for enormous lengths of time compared to human existence, but in the end, they all die. They must use up their nuclear fuel and end their lives. And the sun is no exception.
The sun is probably going to go with a whimper rather than a bang. We're about halfway through the life of the sun. We'll wait about 4.5 billion years more before the sun begins to show its signs of old age, and the sun begins to heat itself up in the center so greatly that the radiation simply can't get out fast enough. And the result is that the outer region of the sun, as well as the core, but primarily that outer zone where so much of the energy is trapped, begins to expand.
As the sun expands, it will become a red giant, enveloping the inner planets. Our seas will evaporate, and life on Earth will be consumed by the sun's outer heat. The star that gave our planet life will take it away. But as one small light is extinguished in a galaxy of billions, new stars will blaze in the darkness. Newborn suns of the Milky Way contain the ashes of stars that have died. What began as stardust gave birth to life. What else the universe may hold is the stuff of dreams.